See it.
Okay. All right. So I'm going to start then. So welcome to the first of the Stony Brook Motorsports new member lessons. Thank you all for coming. This is the first of a few lectures we have planned over the next couple weeks. Tomorrow we have an engineering theory lecture at 11 a.m., as Red said, taught by Red. He will give a speed run of the mechanical engineering curriculum focused on motorsports. So first of all, you don't need to memorize this. It will be recorded. You will have access to the information later. You also just learn this as you go along. Um, and while you do not need to memorize it, um, optimally we'll learn this as you go along, and you'll learn it well enough to present stuff at the design competition we mentioned. That'll be in December probably. The most important thing to take away from this, honestly, is to document everything you do. Um, it prevents having to redo things or find things that you already did. Um, and people in the future can have a stronger understanding of things that you created. So every year we compete at a competition held by SAE International, which is the Society of Automotive Engineers, against over 100 other teams. The main event is an endurance race, but there is also a design presentation. Using that presentation, the judges evaluate the implementation of the design cycle. Um, sorry, I had to admit some. I lost my spot. The implementation of the design cycle, and the cycle shown here is the exact one that they grade us on. So I'm going to use this cycle specifically to go through what we're going to do. So last year, SAE implemented a new rule for the 2020 to 2021 season that stated that all cars must be able to power all four wheels. Before that, we always ran a rear-wheel drive setup, which meant that only the rear wheels on the car had to be powered. So this meant that we had to place gearboxes in the front, and also axles had to be placed in the front, which caused a lot of problems for other systems that had to also package their stuff that was originally there in different places. So like the suspension had to change. And I'm going to go through this some of the suspension changes as examples for the design cycle, because that's what I worked on with Nikita, our suspension lead. So the first step is to define the specifications. Essentially, this means that you have to have the purpose of the component, the needs it fulfills, and the general requirements or must-haves for the design. Sometimes, like in our senior design projects, this is referred to as the product design criteria, or the PDC. Some of the examples of these requirements could be the dimensions, rules, regulations that apply to your component. Furthermore, the cycle talks about this in system, subsystem, and individual component levels. You need requirements for each level, and you need integration throughout, where the systems will communicate with each other and make sure everything fits well. And like again, in places like the nose where everything's really tight, you're gonna have to make concessions and for other systems. So as I said, as an example, I'm going to use the front suspension, and I'm going to use the upper control arm, which is the lighter colored one here up on top. You can see it here. It's an A. It's also called an AR. So I'm going to use kind of an abridged version of the whole process that we went through, because there are a number of complete 180s that we had to do for some of the stuff. But I'm going to focus on the upper control arm because it's the one that ended up with the shock, as you can see here. This is the final one that we have. So we initially placed it on the lower control arm, but that had to change because absolutely originally it had to change because this red line represents where the axle now sits. You can see up here it goes exactly where the shock was, and here you can see that the blue line is where the steering components go now, and that's why we couldn't just offset it on the lower one. So next would be the research and possible solutions. So some general methods of researching would be to find existing patents for similar products, or observe competitor products, or review the history of your own product. And really the first thing you should do is review the history of your own product to understand previous decisions. If you don't know what you have and why you have it, you won't be able to improve upon it. Another thing, Google has a good patent search engine where you can see what other people have done previously, all their original ideas, things like that. And then you can also gather competitor products, and you can reverse engineer them or tear them down to see how they work. Um, so this is a more Baja focused version of the research that I did specifically. So first, it's important that you understand the component you're modifying. You need to know what all the parts do on it, the reasons for the dimensions, and all the locations of things. For the control arms, it's usually a triangular structure like you can see up here, because that's the strongest way to make them. Um, and they have this cup up here holds the ball joint that allows for suspension movement. And then over here we have tubes for pivots, and those act as hinges on the frame. Um, it's also important to know how it moves, like I said, and how it interacts with the other parts of the car. Um, the next step is to investigate previous designs. You got to look for documentation on design decisions that led to the creation of the current part and even past parts. This may prevent a lot of research and testing on things that people already determined aren't feasible. Sometimes the fastest way to answer these questions is actually to talk to alumni because they will give very valuable insight and they really want to help because they really care about the team. For example, for the control arms, I read a whole ton of files, ended up with a bunch of questions anyway, and then I talked to the alumni, and they gave some questions some answers that were kind of different from what I was expecting, but they were like, I could have kind of skipped some of that just by asking, but it's really important to ask them. They're not, they're really nice to talk to, and they will answer your questions pretty quickly. Um, Next, you want to do some research into what other teams do. This is a competitive series, so you want to see what works, what's common, what just doesn't work. You might see a car like you might see like these certain teams do really well all the time, and they have like one component. Um, so then you want to look to see what they do sometimes. So for instance, I looked at competition photos to see what people did for control arms, and I looked at cross members, which is this piece right here going across the A um, to see who uses it and who doesn't. Um, and then after that, you should look into what the pro solutions are and what um, people do in the actual car industry as industry standards. This can give you a lot of insight as to what people do professionally and with it. It might not always be applicable because it's a larger car, but you can also even look into some recreational vehicles because those components are smaller and they might have a similar solution to the problem that you're trying to solve. Um, and finally, you got to try to understand all the information you gathered. So you got to ask questions and then you got to answer the questions based on what you're trying to figure out. So for instance, I made a whole multiple documents, just like a list of questions that I've had after all my research, and I ended up um, answering a bunch of them, and then I'd cite my sources. That way, I could always go back to that. Other people can go back to that, um, and yeah. So these are some of the things I found from looking into pictures, both on our drives and from competitions. So this top left one is actually another team's finished all-wheel drive design that I found that was actually pretty early. And then this one right here is a completed all-wheel drive car that another team used, which has a lot of unique geometry to it. And then the next two to the right were just cars that I found the control arms interesting on. And then the bottom two were well, not prototypes, actual models of, well, the model and the actual thing of control arms that we used to use that were adjustable. And I found out that those were not um, feasible or smart to use anymore. And I was actually looking into that, and that's the thing that I was talking about before with the alumni telling us not to do something because they found out that it doesn't work right. But we were looking into it. So next, you want to select the best conceptual solution to your problem. Typically, we'll write full descriptions of each of the options, pros and cons. You can use a comparison method like a Pube matrix to weigh all the options. Pube matrices are favored by SAE judges, and we previously chose our tires using one. In the matrix, a component will gain or lose a point in a category based on its comparison to the item it's replacing. Optimally, you should eliminate any impossible ideas before even getting to the stage. This would include things that are like not manufacturable. This was relatively simple for the control arms because we already knew we weren't changing the overall suspension design. The length of the control arms didn't really change. The tubes and the basic shape didn't really change. It was just that we had to move this mount over a bit. So that was actually really simple in theory, but in practice, it was a little bit more complicated to get the same strength exactly to match the strength of the old one. So you want your first design to meet the specs that you set as well as possible. So the first design may not be perfect, but it should check all your most important boxes. So you want to rank all your requirements for your design, and then say you want to meet these specific ones, and then you hit those boxes first. And then as you iterate through the process, you work to get to the other goals. So for the control arms and a lot of other motorsports components, you should start with the basic geometry. We started by adding more tubes to allow for the placement of the mount in the desired position, as you can see here, this outer section. Then we spoke with design, fabrication, CNC, and welding to determine if we can actually manufacture the part. We spoke with Red, who welds the tubes, and he said that these angles here are actually too small to get to weld into. So we had to redesign it without those. And then we also spoke with Zoni, our design lead, and he told us that this sharp bend actually isn't possible, and we can't buy that, we can't make that. So we had to do a nice smooth bend like this one. And you can see over here, it's kind of hidden right here. But so then finally, you have to make sure that all your dimensions and measurements are correct. To do this, you might want to put the part in the assembly to see if everything lines up, or take measurements between the features. We worked to optimize the shape to make it smaller and closer to the original triangular shape. It ended up with a wider base, but overall is almost triangular. So then after you design your part, you need to test it using computer software. There are many options to do this, including finite element analysis, or FEA, or computational fluid dynamics, CFD, motion simulations, and design studies. FEA simulates the effect of an outside factor on one part or a small assembly to determine stresses, displacements, thermal characteristics, and more. This can tell you how strong your part is. Design studies and topographical analyses can also show you what section of the part undergo more stress and which sections may not be necessary. This can help you to reduce weight on your part by removing geometry that does not contribute to the structure of the part. So you want to start by thinking about how the part moves and the forces that are exerted on it. Looking at where other components contact the part can tell you what type of force to expect. For example, the control arms contact the frame through the pivot tubes, which act as hinges. The pivot tubes are usually right here, and it just hinges on the frame. That's one point of constraint. Then the shock pushes down on the cross member through the shock tabs right about here, and that would be a force at about a 50-degree angle onto the cross member. And finally, there's the ball joint, which sits here, and that rotates and translates technically, but in order to properly simulate the maximum forces, we just limit it to translating across. Depending on your goal, you may have a force value that you calculated that you want to get to withstand or have the component withstand to a certain degree, or you may want to compare your part to the original design, or like the one that you used on your last car, to say, okay, this one was strong enough, we want to make it the same strength. And then there's another option where you can design something around your system where you want one component to be your weakest component, and then all the other ones have to be stronger than that one. If your part doesn't meet the desired strength, you have to modify the design and make a new revision. Yeah, and then you keep making slight revisions until you finally come to the your desired strength. Whatever testing you do, write it all down. The testing method, questions, answers, results, discussion, conclusions, just like you write a lab report. That would makes it a repeatable, and it shows other people exactly what you did and how to do it in the future. After you simulate your tests, you have to do real world testing. This testing validates or proves your simulations. Without testing, FEA is meaningless. You need to know how accurate your simulation was, if your constraints, forces, and results were accurate. The computer simulation is an ideal scenario, but real-world testing is not. You compare your measured results to your expected results, analyze it, and come to a conclusion. The conclusion may be anywhere from this completely failed back to the drawing board to this is much stronger than expected and we can remove weight from it. After completing your testing, you should write up a report similar to those in labs, and we have a template that you can see here that we use in testing for our testing reports. One example of a possible test would be to test the control arms by sending the car off a high jump repeatedly to determine the max stress and strain experienced. This would theoretically be like a worst case scenario for the control arms. And we would use strain gauges to measure the strain and then use the modulus of elasticity to determine the expected stress. And using the previously simulated maximum rated load, where the control arms will theoretically fail, and this measured data, we can find a factor of safety that tells us how many times stronger our component is than the expected highest stress. So this is basically a shorter version of the full cycle, and this starts after you've already decided kind of what your overall design is going to be, and what kind of concept you're following. So essentially, this is a period of time where you make iterations and revisions of a part, and you keep making small changes until you hit your goal. After you make conclusions about the component for testing, you can either put it into production, redesign it to meet the specifications, or redesign it just to optimize it. You may not optimize it to absolute perfection because we have a limited amount of time, and you should aim to at least meet or exceed your critical goals. And then hopefully everything goes well and we have a successful design end car. That's it. But
Yes, so if there are any questions for Nick, go for it.
So this design process, this is for any time we design anything new about anything?
yes, yeah.
So no matter how small, we do something like that, unless it's like a screw.
So some things, so we wouldn't be designing something like a screw because we have to buy, our hardware has to be a specific grade or either that or we have to have testing done on it.
I mean something like as small as a screw, you know?
Oh, okay, yeah. It really depends. So some stuff you could say, okay, this I know. You have to be able to explain why if you don't do the testing, you know. So you can't test everything obviously, but you have to be able to explain like, okay, I know this isn't going to fail because XYZ, and it has to be a good explanation because they might ask you about it. But something like I don't know, a tab, we don't necessarily do FEI in every single tab on the car. It's like the things that hold every component onto the car. We don't do a test on every single one of those, but maybe we know, okay, from experience we know that these don't break. Yeah.
Thanks.
No problem.
All right, what other questions do people have?
Is there anything particular we're going to be 3D printing for this semester?
This semester, no.
Actually, I wouldn't totally rule it out. We actually have had instances where we've actually 3D printed stuff and kind of tested it to ensure that it kind of works out. Ryan, who is our steering leader, has a 3D printer and printed out a replica of our steering column and the associated U-joints with it just to verify that things would work.
Uh-huh.
So there's a chance for that, yeah.
Okay.
Do we come up with our own criteria and our own scaling system for comparing things?
Yes, but so that's something you kind of learn how to do. So yeah. optimally you will know how to do that, but it's good to have. So, for instance, you can talk to the design lead, Zoni, and he will have good input as to what to like, uh, what it needs to have. And usually, you like since it's a whole car, so you will have set things that you need to meet based on what other people need you to meet. So it's not just going to be completely on your own. It's going to be um, it's really set by what the whole team needs and what your system needs and what your subsystem needs. Um, yeah. So you can come up with a lot of stuff yourself, but it's going to be working towards an overall goal, essentially.
Thanks.
Mhm. Any other questions?
I will assume then there are no additional questions. Um, the chat for these meetings has been spot on.
True.
So yes. So firstly, thank you, Nick, for giving me the lesson. I thought that was pretty spot on. With all this stuff, with all these lessons that go on, a lot of it might seem a bit complex, or like some things might seem a little like a bit much, but a lot of the stuff, as Nick kind of pointed out earlier, you don't have to get immediately. A lot of the time it's more important that you know that thing exists. So like knowing that the engineering design cycle exists, and that it's generally like, oh, identify a problem, come up with solutions, design the solution, fabricate it, test it, rinse, repeat. And this applies for a lot of the lessons that will follow. Again, you don't have to get everything, just as long as you're getting the base, as long as you're understanding what things there are. A lot more of the stuff you'll pick up as you essentially do all these things, and as you do a lot more of the work. So if it seems a bit much, don't sweat it too much.
Yeah, you only have to do what you can, what you're confident in doing. Like you can work your way up to doing something bigger. Too.
So are there any final questions?
Yeah, I've got more questions about like my own timing and stuff. Who do I talk to about that?
I would say when in doubt, I guess this goes for anyone with any kinds of questions. If you're ever unsure about who to ask a question to, just ask me, because I'll be able to either answer it or redirect you to the person most suited to do so.
All right, thank you.
Yes. All right. Oh, okay. So in terms of who drives the car at the race/competition, that's a very good question. It's a very complex process, because we have to be able to determine not just who's the best driver, but also who is the most responsible behind the wheel, and be able to really gauge the situation as best as possible. So if there's someone who, like, we only see around like once a month, and every time they're around they've accidentally destroyed our machines, maybe they're not the best for that position. Whereas someone who, let's say, comes down once a week, and maybe they don't know everything, but they're always happy to learn more, those kinds of people will often be the ones who end up being the better drivers, especially because at competition, the drivers really are representing and working with a year's work of work for, like, in our case, like, let's say 30-ish people or more. So it's really important that that person have a lot of responsibility and really be willing to take risks, but not too many.
Yeah, it's also it's also good to remember the more experience you have, like designing and fabricating the parts, that the more likely you're going to know the limitations of the car ahead of time before you even step foot in it. So it's always good to it generally comes down to who has the most experience in general. I would say.
Yeah, we should have tennis ball tires. I'd be down. Yeah, what other questions do people have? All right, so if people don't have any additional questions, again, feel free to always message me on Slack. I actually am not entirely sure if you can just, like, type into the search bar, like, red. Alternatively, you could do Christopher Sherling. I think that should work if you just type in red. I'm not entirely sure. Nick, if you can verify this.
On Slack, yeah, red works.
Okay, cool. Yeah, so nice and simple to remember by. Don't type in Chris, you'll get like 20 results.
True.
Yeah, you can
Yes.
set a nickname. It'll know the at thing.
Yeah.